Hello everyone, this is Mr. Keppel, and this is Phyzr number 8, Newton's third law. This is from the force unit. It is page number 4. In today's lesson, we'll be learning about what happens when two objects interact. And what Isaac Newton said happens is that forces always occur in pairs. And this is called Newton's third law. Now, before we begin Newton's third law, I'd like to start with a review of the other two Newton's laws, that is Newton's first law and Newton's second law. Newton's first law is also known as the law of inertia, and it says that if the net force on an object is 0, then the acceleration is 0, and this is called equilibrium. When an object is in equilibrium, it will either remain at rest or remain at constant speed in a straight line, uniform motion. That's the law of inertia, that an object at rest stays at rest, or an object in uniform motion stays in uniform motion unless acted on by an unbalanced force. Newton's second law is F equals ma. It's an equation that talks about the relationship between force, mass, and acceleration. It says that the greater the force, the greater the acceleration, and the greater the mass, the lower the acceleration. And these are Newton's first and second law. So what's Newton's third law? What does Newton's third law say? This is Newton's third law. The woman exerts a force on the wall. Then why doesn't she fall over? It looks like she should tip over. She's not in a position that a person would normally be standing. Her body is not keeping her upright. In fact, it's the wall that's pushing back against her that's providing that balanced force that keeps her in equilibrium. So when the woman exerts a force on the wall exerts a force back on the woman. And this is Newton's third law. The force that the woman exerts on the wall is called the action, and the wall pushing back is the reaction. So this is what Newton said. He says that to every action there is always opposed and equal reaction, or the mutual actions on two bodies upon each other are always equal and directed to contrary parts. So our objective here is to take this idea and break it down into small pieces. So the first idea that we see here is that Newton's third law says forces always come in pairs. To every action there is always opposed and equal reaction. So the idea is that any time that there's a force, there must always be two forces, for one on one object and one on the other object. That a force occurs when two objects interact with each other. So forces will always come in pairs. You cannot have a single force. There must always be two forces, one on the two different objects that are interacting. So what exactly is a force? So a force is what happens when two objects interact. In this case, the hammer and the nail. When the hammer and the nail interact, there's a force pair that occurs. So for example, when the hammer hits the nail, we notice that there's a force of the hammer pushing the nail downward. And we see that because the nail was pushed down into the board. But according to Newton's third law, this is only half the story. Forces always come in pairs. It's not just the hammer hitting the nail, there's a reaction to that. And the reaction is that the nail hits the hammer. So the hammer pushes the nail into the board. What does the nail do to the hammer? That force that the nail exerts on the hammer? It brings the hammer to rest. So we see that each of these forces is acting. That the hammer hits the nail down, and the nail hits the hammer upward. This is the action and reaction force pair that Newton talks about in his third law. So force is part of an interaction between two objects. Whenever two objects interact, there will always be one force from the first object on the second object, and a force from the second object back on the first object. My question is, which of these forces is greater? Which force is stronger? The force that the nail exerts on the hammer, or the force that the hammer exerts on the nail? And I'd like you to think about that. Which force do you think is greater? When I ask students this question, I usually hear these responses. I hear people say that, well, the hammer has a lot of inertia. It's very, very heavy, has a lot of mass, and so it's very difficult to slow the hammer down. So when the hammer comes in, it's going to take all that inertia and just pound the crap out of the nail. So the nail is just going to be hit with this crazy, crazy force. And you can see that because the nail gets accelerated really quickly down into the board. So a student who thinks that idea would say that the hammer has more inertia. And so the hammer on the nail is a greater force. But by the same reasoning, to say that the hammer has a lot of inertia, realize that the nail is stopping the hammer. With all that inertia, the nail is able to stop the hammer. So then they would say that the nail is exerting a stronger force since it has to stop this massive hammer. But if you realize what's happening here is both those statements are true. And that's because both forces are equal in magnitude. The hammer, with all of its massive amount of inertia, pounds the crap out of the nail, and the nail has to stop all the inertia of the hammer. And so we realize that the only possibility is that both these forces are equal. And if you don't know what magnitude means strength. So it means don't worry about the direction, just focus on the size of the force, the magnitude. So these two forces, the action and the reaction, are equal in strength. They have equal magnitude. Another way to think about it is to say that since both objects are part of the same interaction, there's no other possibility than for them to both have equal magnitude since they're part of the same interaction. So what if we don't look at the magnitude? What if instead we look at the direction? How do the directions of the action and the reaction compare? How do the directions of these forces compare? The magnitude of the forces were equal, but the directions are not. Notice that the action force points straight down and the reaction points straight up. So the action and reaction, the force pair, are opposite in direction. The two forces are opposite in direction. The direction opposes the other direction. So to put it all together, Newton says that the action and reaction forces are equal in magnitude, but in opposing directions. When you punch someone in the face, their face punches you in the hand. That's Newton's third law. Since a force is part of an interaction between two objects, if one object exerts a force on a second object, then the second object exerts a force on the first object. So the glove exerts a force on the face, then the face exerts a force on the glove. That's Newton's third law. Here's the action, that's the force on the face by the glove. Notice how this is written with subscripts. So we write the force on the face, it's the first letter is the one that it's on, and the second letter is the object that it's by. So this is the force on the face by the glove. That's the action. So what's the reaction? The reaction would be the flip of that. It would be FGF, or the force on the glove by the face. Here it is one more time. There's the action and the reaction. Let's put this all together into one epically long sentence that's going to be Newton's third law. Whenever one object exerts a force on a second object, The second object always exerts a force on the first object of equal magnitude and in the opposite direction. This is Newton's third law. We have to write it out this way because we want to make clear that there are two objects that are interacting, and one force is on the second object and the other force is on the first object. The action and the reaction do not act on the same object, they act on different objects. They act with equal strength in opposite directions. So one more time, whenever one object exerts a force on a second object, the second object always exerts a force on the first object of equal magnitude and in the opposite direction. If we use the notation that we just discussed, we could write it like this. We can say that the force on object B from object A is equal to the force on object A from object B, but in the opposite direction. And that's what the negative is for. This is probably a much easier way of expressing Newton's third law than writing it out grammatically, but it's still important to understand that there are two objects interacting. So a lot of people would say that for every action there is an equal and opposed reaction. But if we say it this way, we kind of forget about the two objects that are involved. In fact, I've seen people who mistakenly believe that the action and reaction, since they're equal, that they cancel each other out and that there's no net force, that an object will be in equilibrium. But what you must understand is the objects that are interacting each experience their own force on them. Object B experiences a force from object A, and object A experiences a force from object B. The forces act on different objects. The net force on object B is the force from object A, and the net force on object B is the force from object B. They do not cancel out because they're acting on two different objects. So that's why it's important that we write Newton's third law out in full to recognize that the forces are acting on two different objects. It's not just action-reaction. It's a little bit more than that. So here's an example. A bullet is fired from a gun. We wish to identify the action and the reaction force pair. When we write out a sentence to say what the action force is, we must always include the two objects that are interacting, some sort of a verb, either a push or a pull, and the direction that the force is acting. In this case, the two objects are the gun and the bullet. Now, what does the gun do to the bullet? Well, the gun pushes the bullet. A force is either a push or a pull. We wouldn't say that the gun fires the bullet because that wouldn't be a force. A force is a push or a pull. So now we have that the gun pushes the bullet. But what direction does the gun push the bullet? In this case, the gun pushes the bullet forward. Now, you could also have said it right, but I think that forward is a more generally correct term, that whatever direction the gun is pointing, the bullet is always pushed forward from that direction. So what's the reaction force? If the action is the force on the bullet by the gun, then what's the reaction? To find the reaction force, we just need to apply Newton's third law. Newton's third law says that when one object exerts a force on a second object, the second object exerts a force on the first object in the opposite direction. So if the gun pushes the bullet forward, the bullet pushes the gun backwards. So that's the force on the gun by the bullet. And you can see this from the recoil in the gun, that the gun also gets pushed backwards. Not only does the bullet go flying forward, but the gun gets pushed backwards. The question for you to think about is, which force is greater? The force on the bullet that sends it flying forward, or the force on the gun which sends it recoiling backwards? Which force is greater? Newton's third law says that the action and the reaction are equal in magnitude and opposite in direction. So the force on the bullet, the force on the gun, they are the same. The bullet and the gun both experience an equal force. They both accelerate. This is a little bit confusing because you think the bullet goes flying at the speed of sound and the gun barely goes back at all. How could these forces have been equal? So why does the bullet move so much faster than the gun? Can you explain this? If the forces are equal, as Newton's third law says they are, how could the bullet move so much faster than the gun? The trick is to realize that the bullet and the gun do not have the same inertia. The gun has a lot more inertia than the bullet. So if we start with Newton's third law, which says the force on the gun is equal to the force on the bullet, we'll apply Newton's second law, which says that the mass of the gun times the acceleration of the gun must be equal to the mass of the bullet times the acceleration of the bullet. But realize that the gun has a large mass and the bullet has a small mass. So if we substitute in large and small mass, notice that the accelerations have to balance so that the forces stay equal. So a large mass of gun, or a lot of inertia in the gun, gives it a small acceleration. But the same force on a small mass gives a huge acceleration. So the bullet goes flying with extremely high speed because it has a greater acceleration due to its smaller mass. The forces are equal, but the masses were not, and that's what contributes to the difference in motion. The bullet accelerates more than the gun because it has a much smaller mass. It's important to realize that we don't see forces with our eyes. We see the changes in motion. We see the acceleration with our eyes. So it's very easy to think that the bullet gets pushed harder because the bullet accelerates more. But you have to remember that a force is not acceleration. The force is mass and acceleration. We must remember that the mass difference will contribute to an acceleration difference since the forces are the same. Here's some more force pairs to practice. So let's consider an apple that falls to the ground. What's the action and the reaction? Let's identify the force pair. So what's the action and what's the reaction? If you're having trouble, let's put up the little framework fill in the blanks that I had before. Object A pushes or pulls object B in a direction. So we should start off by asking ourselves, what are the objects that are interacting? When an apple falls to the ground, well, obviously something is pulling the apple. But what? What is pulling the apple? And it turns out it's the earth. The gravitational pull of the earth pulls the apple down. So what's the reaction to this? I'll let you think about it. Believe it or not, the reaction is that the apple pulls the earth up. And this is true. This is a direct result of Newton's third law. That when an apple falls to the ground, the earth pulls the apple and the apple pulls the earth. So which force is greater? Newton's third law says they're equal. So why is it the apple moves and the earth doesn't even budge? if the forces are equal, if the apple's being pulled equally to how the apple pulls the earth, why doesn't the earth move? Why don't we see the earth move? And the reason is because the earth has a huge mass. So that force, which was strong enough to pull the apple down, isn't even nearly strong enough to pull the earth up in any noticeable amount. The forces are equal. Here's another one to practice. A bowl rests on a table. Identify the force pair. What's the action and what's the reaction? The two objects interacting are the table and the bowl. So the bowl pushes the table downward, and the table pushes the bowl upward. Remember that the earth is also pulling the bowl downward. And so it's this upward push from the table, which balances the downward pull of gravity, so then the bowl stays at rest on the table. So which force is greater? The bowl pushing the table or the table pushing the bowl? Which force is greater? Newton's third law says they're equal. Let's try another one. A sliding athlete slows down. Identify the force pair. What's the action and what's the reaction? The two objects interacting are the ground and the athlete. The athlete pushes the ground forward, and so the ground pushes the athlete backwards. And that's the reason why the athlete slows down. It's this backward push from the ground which decelerates the athlete. Now, which force is greater? The force of the athlete pushing the ground or the force of the ground pushing the athlete? Newton's third law says they're equal. And here's our last example. A sailboat sails forward. Identify the force pair. What's the action and what's the reaction? The two objects interacting are the sail and the air, or the wind. So the air pushes the sail forward. In response, the sail pushes the air backwards. So the sail actually slows the air down. The air can't push through the sail, so the air actually gets slowed down. So not only is the boat getting pushed forward, but the boat is taking this push from the air and using it to propel forward, and in response, the air actually slows down. So, which force is greater? Newton's third law says forces are equal. So that's it. That's Newton's third law. To every action, there is an equal and opposed reaction. Whenever one object exerts a force on a second object, the second object always exerts a force on the first, equal in magnitude and opposite in direction. I hope you've enjoyed this Phyzr. This has been Mr. Couple, and I'll see you in class.